One of the probability model which confuses a little bit is log normal distribution model. So when I give you a lecture this morning, of course I'll deal with a normal again. Normal is very straightforward. Then also the log normal distribution, and pay attention on the log normal distribution function. All right, so let's see. I think today I can finish this up. Okay, today I'm going to give you 3 more models that will conclude the case. That will conclude the case. This is case 4. And you have actual stress. Actual stress has a probability model, and yield stress is a deterministic situation. And here we're going to look at again the normal probability model. Whenever you hear the normal probability model, which is most simplest and usually can get the closed form solution, then you can easily compute and all that. And for the actual stresses, for the normal, I use the capital letter, the sigma S, and sigma is equal to notation, kind of the tangling up, it's not simple. Subscript and again subscript of the subscript. Who cares, right? And case 5 for the log normal case, I'll give you some update for the notation, so pay attention on that also. So here, what's the B subscript, this capital sigma S? What is this? I want to make sure we don't confuse. Okay, what's this? B. Who cares? Who cares? Come on. EXP is a normal distribution function, minus half, and sigma minus mu sigma S, B. Let's straight up the notations, because I screwed up myself when I look back again. This is a probability density function of Gaussian distribution, or you can say normal distribution, Gaussian probability density function. Okay, so here, what's this? This one. Mean value. Mean value of actual stress, right? I want to make sure you don't confuse for normal, log normal. It's slightly confusing. And B is what? Standard deviation of actual stress. So this is the same thing on that. And the F sigma S, sigma, what's this? 3. Cumulative distribution function, the Gaussian cumulative distribution function, which is integration of this guy, density function, of course. So then this is a constant. So in the exam you have to have integration, simple integration. I haven't made up the problem set yet. So, but that's what we have to do. So minus infinity to sigma and exp and the whole thing this goes right into here. I wanna write up because minus half, and this I'm gonna use a t, or this is integration parameter, so I happen to use a t here. I use a sigma, that's not right. So mu sigma s over b sigma s dt. So this is nothing but the integration parameter. In my note, I use a sigma c, so they make a correction. This integration parameter. So this is what the Gaussian cumulative distribution function for integration. Then to make easy for calculation, then you use a standard normal distribution by integrating the error function. So I can say this is simply phi So over here, what's the expression for phi? I use x, let's say, in general. This is 1 over square root of 2 pi and integration minus infinity to x exponential function minus half t squared dt, right? So this makes this very easy. This is really standard. So all we do here is if you this is a function and this is like an x function. If you have a normal distribution, something like this, at the mu x, you simply put it back to the case and change into that forms, right? Standard normal distribution function. Then here, you can just look at the table. For MATLAB, you have a function there. You can simply get the number from there. So yield stress is, of course, deterministic value. So yield stress is deterministic. So this is simply deterministic. In fact, in the actual situation, in reality, you can make resistance. Yield stress is a part of the resistance or strength. You can use comfortably the deterministic value for the computation. Okay? Sorry to point you, don't feel bad, That's nice. That's the sign you really work hard last night. Shungan is a little bit... Okay, so then the reliability expression is a probability of what? Sigma S, sigma Y, which direction? This is larger than this, or this is larger than that? Sometimes confusing, right? Sigma S is the actual stress, always lower than the yield stress or strength. So then here this is once you write this, you can cast into the cumulative distribution function. So here, this is for capital sigma S. So now this is, we have done it over there. So then you can have, which is a phi. So now we have to replace sigma by sigma y. So sigma y, mu S over B sigma S. So now this is, when you get there, you can read off the number from the table, things like that. And then R can be finally replaced with the value. Sigma y is a deterministic yield stress. It's a deterministic value. And mu is same as using same notation. This is mean or expected value of e to the s. And the B sigma is standard deviation, which is a variance of the actual the stresses. So here you know this, you know that, and you know that. Then you can read off the table or calculate the error function, then get the reliability. So once you have a reliability or probability of the survivor, then probability of the failure is simply 1 minus R. So the table is concerned, I think I included in the probability model, or you can have, it's in the back of the book, everywhere you have. So bring that table in. And this you can divide here up and down by expected value of actual then stresses. Then you can express this guy in terms of N1. What's the N1? central safety factor. That's what you use. Central safety factor. So this is N1 minus 1 B sigma S. You divide everything. So this is the resistance over the mean actual value. You divide it by that. Then what happened on the bottom? Bottom is as is. Is it correct? It's not correct, it looks like. So if you divide it by that, you have to, over here, this guy divided by this, right? So make a correction on your note. Then what do you call this value? Coefficient of variation for actual stress. So this I can write this guy as that. So let me rewrite here. So it's a coefficient of variation for actual stress. If actual stress has a loss of uncertainty, what do you expect to this value? If this value is like above, like a 0.5, which is a 50% to the COV, then that's really bad. That's really a loss of uncertainty in there. For the probability model is concerned, a very flat model. So then when this value is small, you are dealing with the actual loading, not well-defined loading. If this is very small, then what? Then you know the uncertainty is not much. Okay? So if this is large, what do you expect in terms of the R, reliability? Very bad, small, vice versa, okay? So if you know, this is the final expression. So now R has directly connected to N1, the safety factor. But if you just use inverse notation, you know, so you can express N1 as 1 check back again plus mu sigma S phi inverse the R. For the specific value of R, then you can compute the corresponding the central safety factor. If this value is large, then this guy really blow up. So then you know you pick up the wrong model. So you pick up the wrong model. So as example, how to pick. You remember this table? Or nowadays everybody carrying the smartphones or whatever, when you can put that in, you can get the value. Normal distribution is, I'm not going to bother you. You take a look at page 711, 710, then you can have that. Yeah, but don't be screwed up. I'm going to give you the problem, of course, normal distribution. I announced it. If you still make mistake, too bad. There is no such a thing as a partial point. Why? It's so obvious. You can't afford to make mistakes, right? Yeah. Okay. Now a log normal distribution. Case 5. Sigma S is random. Sigma Y is deterministic. This model is a log normal. Very close to the normal distribution. Log X follows the normal distribution. So here, for example, if you look back, another section, okay. Y, if X follow log normal distribution, and this guy follow what? Normal distribution. That relationship is what all you have to remember. It has a one-to-one relationship. So again, cast into the probability model, and 1 sigma B sigma S 2 pi exponential function minus natural log of sigma minus, I'm going to use A sigma S, make a correction in my note which Higyo sent out to you. I used notation. I used the notation like mu sigma S. That confusing part. So change. Change that to A subscript sigma S. And 2B sigma S square, and this guy square. Of course, sigma is greater than 0. Over here, there is a B, there is an A. Here, A sigma S and B sigma S is equal to the mean and standard deviation of you see, I wrote of natural log sigma S. Okay? It's not the sigma S, but natural log of sigma S. So pay attention on that. Otherwise, it's all same. Otherwise, everything's okay. I think it should be correct. You can check that. sigma s sigma is equal to 0 to sigma 1. I'm going to use a t b sigma s 2 pi exponential function. After that is very close, very same to natural log t minus a sigma s b sigma s square. dt is an integration parameter. Okay. P1, any question? Question? Speak. I could screw up. I look back yesterday afternoon on this and gosh, I better be careful. So I changed to A. This is a B. This I guarantee I'll give you the problem. Whenever I screw up, I usually put that in the exam problem. This is, you will get the problem which uses log normal and the normal probability density function. Then if you just look at, that's all you need. You don't need, I don't want you to screw up when you really do the calculation in reality for your problem. So now we can cast to standard normal distribution function. Then you can make the life much easier. That's all we're gonna do. So we're gonna say let, or substitute let natural log t minus a sigma s over sigma s. I'm gonna say let that's equal to z. This is a process to get into the slight transformation to standard form. So then f s sigma is integration from 0 to this guy is ln sigma minus a sigma s over b sigma s 1 over 2 pi. Standard form, standard deviation is 1 and mean is 0. We just transform into that form. That's all we do. So exponential function minus half z squared dz. Back to the same form. So this is equal to phi function natural log sigma a sigma s b sigma s is that. Then now you are ready to define the, not to define again, well define and get the expression for the R. Okay, R is equal to, you have to make a correction on my note, change mu to A, right here. Now this is reliability, so which is a probability. Sigma s is less than sigma y is equal to f sigma s fy. So A sigma s is mean of natural log of sigma s, random variable. So we are looking for, really what we are looking for is mean of ES, or this is equal to, that is equal to the mu. This is what I want to eliminate, the confusing point, right? So this is equal to this. So A sigma s is equal to mean of natural log sigma s. That's a little bit confusing point in the log. Well, it's not really confusing. I confused. So, you know, I want to make it very clear. And this is expression. I didn't derive this expression. You can find any place, or you can do yourself as you wish. Is equal to exponential function A sigma s plus half of B sigma s then you can get this guy is e to the es over sigma y. Then of course you can, this is a deterministic value, and this comes right there. You can get central safety factor. So variance of ES is equal to exponential function 2A sigma s plus B sigma s Take a look at this. The possibility I screw, well, I don't want to use a screw up, misspell out. Check it out. This I need a more bracket, because exponential comes here. If I write this way, this could be, whole thing could be under exponential. So this question mark, I'll of course clarify by looking at my notes of book. You know what I'm saying here? Exponential function. Or you can look at the Wikipedia, log normal. and this exponential function is up to here. I think I want to clarify Monday, but not clear. Take a look at anybody has iPad 2 or that kind, then you can really check right away whether this is where the bracket is missing. I feel if I just write this can apply only this multiplied by the EXP. So that's questionable. We're gonna do that. So R expression for R in terms of this, if you look at my note, it is something like up to here. So that you have my notes, right? So it's so long here. You can rewrite this simplify using the coefficient of variations of sigma s, and you can do that. Check. So handy, you know. Can you believe this? Everything is here. That's why when you walk, crossing the street, all looking like this. Gosh, stop! I talk to the, stop! There's car coming. So small, I can't even read. Yeah. Okay, let me write. Here is answer. Okay, oops. Variance. Okay, so this is a correct expression, and here is e to the 2 sigma plus sigma square. How do you do that? It just appears just to close it. Okay, this is 2 mu square. This is sigma square. Come on out. Come on out. Don't say I don't know.
Here we have to square.
Oh, square it, yeah. So from the beginning, this has to be square. This has to be square, right? Thanks. So this has to be square. It disappeared again. Maybe put it. Sorry, but make a corrections, okay? Boy, my phone. I think this looks fine here. Compare this. I'll check back once again. I'll check back. See, still notations are. Yeah, that's a square. Has to be there. Variance b square has to be there. I think that's square. check back this guy. So it should be fine. Okay, I think looks like I'll check back. I want you to check back. Then if there is any correction to do for the log normal distribution, I'm gonna announce it on Monday. Okay, last model I want to pursue is Weibull distribution. In my note, case number 6, I didn't include when we talk about the probability model. So the Weibull distribution is a part of the family called the extremal distribution. I just use one and the special case of the Weibull distribution when you set one of the parameter as a 1, which really converge into the exponential distribution. So the case number 6, Isaac, he put that in, but I don't know what's the big use of it. But this is another kind of the Weibull family. So I'll skip the case number 6, and you can take a look at it. And the case number 7, if you look at the case number 7, there is the Weibull distribution, 2-parameter the Weibull distribution, which we learned in the probability model section we did some time ago. So here I'm going to cover case 7. So if you take a look at the case 7, that's a 2-parameter, the Weibull distribution. So Weibull distribution in the book, final equation is also not correct, and that I will announce it. And of course I want to redraw reset the table in there because it could be wrong. Case 7, final question, final case. Sigma S is a 2-parameter Weibull distribution function. Of course, this is deterministic, constant. Final case. And actual F sigma S, sigma is equal to 1 minus exp minus sigma over the C sigma S. This is a 2-parameter. Sigma is 0, and of course K and C sigma S is greater than 0. This is a 2-parameter. You can just tweak the 2-parameter to fit the actual data set to fit in. So this is a distribution function. And once you get that, as we always have done, that is equal to same exp minus sigma y is a 1 point C sigma S K K. Others are all the same, which is coming down. So this, and of course, in terms of the probability of the failure, is this parameter relevant to the reliability model is again like a mean and standard deviations. You can get the skewness. You can really plot all that. Okay, so here is a mean. Mean of sigma s is equal to sigma s gamma function 1 plus 1 over k. Again, C and K, you determine, not nobody else gonna get you. You fit your data set to the probability model. If it fits well to Weibull, two-parameter Weibull distribution, then you can do that. Variance is equal to this is a pretty checked up because the result was not matching the my calculation, so this is all pretty well checked up. So R is now, again, this is Fs sigma y is equal to 1 minus, already model is done, and minus sigma y c sigma s k. Of course, sigma y is less than equal to 0. So here, this guy can get it from right here. Express this expression into this is equal to this. So C sigma s is equal to mean over gamma function. Then you can determine in that expression. And R is equal to 1 minus exp minus sigma y gamma 1 plus 1 over k e to the sigma s is okay. This is correct expression. Then in terms of N1, then R is equal to 1 minus exp minus n1 gamma 1 plus 1 over k You have to be careful because there is a number of brackets here. So, which is K is here. This is correct expression. Isaac's book, he made a slight mistake. So here is a sigma y is z. Then n1 expression with r. n1 is equal to, you can just manipulate this equation to get that. And this is equal to gamma 1 plus 1 over k, that to the k power, and the natural log 1 over 1 minus r. So r is concerned here, which is a specific r. Specific r means it's like a required reliability value, assigned value for the reliability, and this is a correct expression. And the last page I said homework, the table 3.2. So homework, the table, this is homework number 4, table 3.2 and figure 3.5, reconstruct based on this correct the equation set. Maybe same, maybe he just could write the equation wrong. Just the k was, somehow he forgot, he dropped the k, but this has to be back in. Then reconstruct the table 3.2 and the figure 3.5 and check that out whether it's different from the shown in the book. Okay.